Time series analysis changes the game because the ordering of observations now matters. In cross-sectional data, the position of an observation in the dataset is irrelevant. In time series, the fact that one observation came before another is part of the economics itself. That difference affects how we think about randomness too. A time series dataset is one realization of an underlying stochastic process. We do not have many interchangeable draws from a population in the same way we do with cross-sections. Instead, we have one ordered sequence evolving through time. The simplest time series model is static. In a static model, current y depends only on current x. If x moves today, y moves today, and that is the end of the story. This can be useful as a baseline, but many economic relationships do not work that way. Policies, prices, and expectations often take time to have their full effect. That is why finite distributed lag models matter. In an FDL model, yt depends on xt and on lagged values, like xt minus 1 and xt minus 2. This lets us describe dynamic adjustment. A tax change today may affect behavior immediately, then continue to affect it next year and the year after that. The coefficients in an FDL model have a natural interpretation. The coefficient on current x is the impact multiplier, or immediate effect. The coefficients on lagged x terms describe delayed effects. If the change in x is permanent, we add those effects together to get the long-run multiplier, which tells us the eventual total effect after the adjustment has worked through the system. This is why dynamic models are so useful. They let us distinguish between short-run and long-run responses. A policy could have a small immediate effect, but a large eventual effect, or vice versa. Without lag structure, those two possibilities get collapsed into one average relationship. At the same time, lags create their own estimation problem. Economic variables often move smoothly over time, which means current and lagged values can be highly correlated with each other. That creates multi-collinearity and makes individual lag coefficients noisy, so we may understand the overall dynamic pattern better than we understand each separate lag coefficient. Time series regressions also still need all the usual specification care. We can use logs, interactions, and dummy variables. Seasonal dummies are especially important for quarterly or monthly data. And time trends can absorb broad upward or downward movements that would otherwise contaminate the regression. Trends deserve special attention because they can create misleading relationships. If two variables both trend upward over time, a regression may show a strong association even if neither one is actually causing the other. This is one of the reasons time series econometrics becomes much more careful about stationarity and persistence in later topics. So the key ideas are these. Time series analysis is about ordered data generated by a dynamic process. Static models describe contemporaneous effects. Distributed lag models describe delayed adjustment. Impact multipliers and long-run multipliers help us interpret those dynamics. And trends and seasonal structure need to be modeled explicitly if we want the coefficients to mean what we think they mean. Time series econometrics becomes powerful once we stop thinking only in terms of one-period reactions and start thinking about how shocks echo across time. Next, we push further into stationarity, weak dependence, and the asymptotic logic that makes OLS workable in dynamic settings.